Hey, it's Hawken with Top Don. Today we are going to take you through a misfire diagnosis on a Pentastar platform. The Pentastar platform is the 3.2 and 3.6 liter engines on Chrysler products. And again, we're going to walk you through a diagnosis on one of those vehicles. However, most of the principles in this video can be applied to a wide variety of vehicles. And just the only things that are really context specific are the origin of the fault itself. The origin of the fault itself is very common for this platform, but the testing methods and everything else we talk about is absolutely applicable to other vehicles. So let's go ahead and get started. So our vehicle today is a 2015 Chrysler Town & Country 3.6 liter V6 engine. The concern is the vehicle has been to a previous shop and had a large number of components replaced in an attempt to resolve a misfire. Now, the list of the components known to be replaced at the previous shop include a crankshaft sensor, at least one, if not more, camshaft sensors, all 6 ignition coils and spark plugs, and the cylinder head was actually removed and sent off to a machine shop. This is the minimum of what we know has been done on this vehicle prior to us looking at the vehicle. So the tools that we're going to use in this particular video include the Phoenix Smart as well as the Phoenix Oscilloscope. It is important to remember you can use any Phoenix Professional Series tool with the Phoenix Oscilloscope to perform the tests we are going to show you in this video. The additional tools we used primarily consist of a pressure transducer. Now again, it's important to remember there's a difference between a pressure transducer and a delta sensor. Pressure transducers measure actual pressures. Delta sensors only measure the dynamics of change in pressure. We're also using a high-range amp clamp, which would be 600 amps or greater is necessary, and that's going to be used for our relative compression test. And then an ignition coil on plug probe. Again, it's not important what specific tools we used. With regards to those, you can pick whatever type of these you like. So if you have a specific transducer you like, you can use that with the top-down scope. Same with the amp clamp, same with the ignition probe. So the first thing we do on any vehicle we look at is we pre-scan the vehicle. We always need to confirm the concern that is being communicated before we attempt to figure out what's wrong. So we pre-scan the vehicle, and sure enough, the primary fault we see stored here is a P0301, which is a cylinder 1 misfire. Now, I have blurred out another fault, which was caused specifically because the mass airflow sensor was unplugged with the key on engine off, and so that did set an additional fault code, but that does not have anything related to our problem. So, after we did the pre-scan, we went into the OBD2 data stream. Now, if you're not familiar with where to find misfire data in the OBD2 mode of your scan tool, go to our top-down channel, and we do have a video specifically showing you how to access this data. We went into the OBD2 data, and we did clear the faults before we attempted to start the vehicle and confirm that it was misfiring on cylinder 1. And after we restarted it, we got it to count misfires on cylinder 1. So you see we have 358 misfires on cylinder 1 just after clearing the faults and restarting it and letting it idle for a short time. So clearly it is misfiring pretty significantly. Then we went into the Chrysler OEM data stream, and we did look for other clues to see if there was anything else we could pick off related to the misfire. What we noticed was the injector pulse width on cylinder 1 was being shortened up. So basically, the PCM is taking away some fuel from cylinder 1. And this is happening in response to the misfire or a lack of total combustion on that cylinder, right? It's not completely combusting the fuel-air mixture, and therefore the PCM is subtracting fuel from that cylinder. So this confirms that it is in fact attempting to compensate for the misfire. So the first test we're going to do here is a relative compression test. Now, many vehicles support what we would refer to as clear flood mode. Clear flood mode, basically, you do key on engine off, you hold the accelerator pedal to the floor, and then you attempt to crank the engine. If the vehicle supports clear flood mode, the engine should crank but not start. This should disable the fuel injectors. Now you want to be careful because if the vehicle does not have clear flood mode, it's going to want to rev up really high immediately when it starts up, and that could be bad for the engine. So be careful. That is something that may or may not exist. If your vehicle does not have clear flood mode, then you need to find a method to disable fuel delivery, whether that's unplugging the fuel pump on the low pressure side, pulling a fuse for it, or pulling a relay out. However you achieve that, you have to disable fuel injection to do this relative compression test. Then we're going to place our high amp clamp, so 600 amps or higher, around the positive cable that runs from the battery to the starter. If we can't find that cable or access that cable, then we can put it around the negative battery cable instead. However, if we put it around the negative battery cable, we may need to flip the amp clamp around. When we do the relative compression test, we'll show you what the current waveform should start as, how it should respond when you go to crank the engine, and that way you can determine if your amp clamp is facing the right direction. So just a couple of quick settings on the scope. These will apply to all people using our scope for this test. We're going to talk about the sample rate. We're not going to talk about voltage scaling because that's going to vary based off the specific hardware you use, but we will talk about sample rate. It's important to understand that this scope is fixed sample rate ranges. So this 50/10 is the highest sample rate, and then we have three other ranges here that it can be turned down to. Now, I'm going to leave it on 50/10 because the higher sample rate is going to allow a little bit clearer image when we put more time on our screen. So we're going to do menu, user set, depth, which is sample rate, and then 50/10M. That's our highest sample rate. Then we need to set up our time on the screen, or time base. So what we do for that is we go down to the bottom center here, and you can either click on the time itself, or you can click on these two little pictures of waveforms. So you click on one, and it makes the time on the screen less, and if you click on the other, it makes the time on the screen more. Suffice it to say, what you want to see in this window when you do a relative compression test is either 2 or 5 seconds per division. So if you count these vertical lines on the scope screen, that's your divisions, and I believe there's 10 if I'm not mistaken. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 divisions. So if you have 2 seconds per division, that's roughly 20 seconds on the screen. If we have 5 seconds per division, then that would be 5 times 10, 50 seconds on the screen, right? So you want to keep that in mind as you're doing any test. How much time you need on the screen is based on the type of test you're doing. But in this case, we're going to do either 2 or 5, and that's going to be ideal. So what you're going to see now is we did our relative compression capture. The top window here is the actual capture that we grabbed, and what we're seeing down in this bigger section here is the zoomed in waveform. Now, the other thing you're noticing here on the relative compression is when the current starts flowing to the starter, it goes up. That means our amp clamp is facing the correct direction. If instead, when we went to crank the engine, the current flow started going downward, then we would simply want to go take our amp clamp and flip it over the opposite direction. You can also go into the channel, and there is a setting to invert it, and that would cause the waveform to invert and go the other direction as well. Either one works. I prefer to just flip the clamp. So now, once we've got the waveform captured, we're going to use the run stop button on the bottom right in order to actually get the capture. So basically we'll hit the run button, we'll go crank the engine in clear flood mode, then we'll jump out of the car quick or take, the scope and the tool with us into the car if we can reach. And we're going to hit the stop button right after we capture the waveform. Once we've captured that waveform, we're going to hit that zoom button. And then down on the bottom center here, we can see that our time scale shows both time scales. The top time scale, 1 second, is the original capture as far as how much time per division we had. And the bottom number is what we are currently displaying in this bigger section down here. So we captured it at 1 second per division. And down on the bottom, we're now zoomed into 100 milliseconds per division. So just keep that in mind. What do we see in the capture? We see in the capture here that we have a decrease in compression, right? One of the humps or spikes in current flowing to the starter, in other words, the amount of resistance the starter is facing mechanically to rotate the engine, is decreasing. Now, engines are constructed in a symmetrical fashion. Therefore, the amount of effort that the starter takes to turn the engine should be relatively symmetrical for each individual cylinder, assuming the engine is in good health. Now here, we can see that the engine is not in good health on one cylinder because the current spike is lesser on that cylinder. That means the engine or the starter is not requiring as much effort in order to turn the engine over when it reaches this cylinder. Now, we don't know that that's cylinder 1 because we don't have any ignition sync on this waveform. So we could add our ignition probe and put that on the ignition coil for cylinder 1, and we would then see a ignition spike right here in correlation with this. Now, don't worry, we did do this on one of the following tests, so you will get to see that. So we see that we have a loss of compression on a cylinder. That's bad. Now we're going to take an intake vacuum pulse capture in conjunction with our relative compression test. So, a couple of tips when we're doing an intake pulse capture. Remember, if we are using an intake pulse cap, or we're performing an intake pulse capture, and we use a pressure transducer, the pressure transducer measures actual pressure. If we are using a delta sensor, that only measures rate of change, the dynamics of pressure change, not the actual pressure. So it's very important to keep those two straight. We used a transducer, which is measuring actual pressure and vacuum in the intake manifold. Now, when we set it up, we want to use a short and stiff hose to connect the pressure sensor, the transducer. We also need to get it as close to the vacuum source, aka the intake manifold, as much as we can. So if you can find a vacuum nipple right on the manifold or right by the throttle body, that's going to be ideal. Then, when we go to do the cranking relative compression test with the vacuum capture, you can also use a hard object, something that cannot be sucked in or ingested into the intake tract, like a board, for instance, and partially restrict that throttle opening. So if you take off the throttle boot and you partially restrict that throttle opening, blocking some of it off, that can exaggerate or increase the dynamics of the waveform that you get on the intake pulse capture. Sometimes this can make it easier to read or pick off differences. So here's our intake pulse capture. Again, we're not going to talk about voltage scaling because that's going to vary based on the specific amp clamp you use, based off the transducer you use, and based off the ignition coil on plug probe that you use. Our top capture here is the relative compression. We can see that there is a decline in the compression here again, just like we saw on the previous capture. It's a little less dynamic in appearance here, simply because our scale is smaller. Now, what we also see here is we have an ignition sync waveform on cylinder 1. So we put our coil on plug probe on cylinder 1's coil, which means that this is establishing that this is cylinder 1's compression event. We also know the firing order on this vehicle, if you look it up in service information, is 1, 2, 3, 4, 5, 6. Now, this middle waveform we see here in the yellow is actually the intake pulse with a transducer. Now, remember, engines are constructed in symmetrical fashion generally, correct? So what do we see in this intake pulse that we're looking at here? It's not entirely symmetrical, is it? This is definitely suspicious. Now, the time base that we used to capture this waveform was 2 seconds per division originally. That's our big picture up on the top. And then when we zoomed in, we're zoomed in at 100 milliseconds per division down here. Just a note. Now, there's our lower compression event. What do we see happening right after cylinder 1's compression event? We can see that the engine does not go down into as much of a vacuum here, right? Immediately after that compression peak, we have a lesser amount of vacuum in the intake manifold. Why would we have less vacuum in the intake manifold? Well, we're not sure yet, right? We can also see there's an ascension in the waveform as pressure climbs in the intake manifold. Pressure climbing, but we see that the slope of the pressure rise is less steep right after cylinder 1, and it is more steep on the following cylinders that are presumably in a normal, healthy condition. That's interesting, right? Now, what else do we see? We also notice, and I didn't draw arrows here, but you can see it. As the pressure in the intake manifold reaches its apex after cylinder 1's compression event, we also see that the downward slope is kind of lazy, right? And then we look at the downward pitch of the angle on the pressure in the manifold after the events of other compression on other cylinders, and it's much more steep and linear, right? So again, lazy and slopey and steep and linear is the comparison we see. This is very suggestive that we have a valve train problem, right? So we feel pretty comfortable at this point. This is definitely a mechanical problem. We have a loss of compression. It's a mechanical problem, and we feel reasonably confident that this is in the in the valve train of the engine itself. Here's our notes. Now we're going to do an exhaust pulse capture just to see if we pick off any other differences. Now again, we're not trying to get into the nitty-gritty details of what each minutia of this waveform means. If you would like to get into that level of understanding, there are technical classes available from many instructors that go into the deep nitty-gritty details of these waveforms. Brandon Steckler, as well as Adam Robertson, teach technical classes on these particular types of analyses that can be highly beneficial to gaining a greater understanding of the specifics of what's happening and what it means. Again, the way that I look at these waveforms is very general in a sense of we're looking for outliers. The engine is constructed symmetrically. We're looking for fairly symmetrical waveforms. If we see greater than a 10% deviation in the pitch of the angle, the dynamics of the amplitude, right? Higher or lower points of any individual waveform in relative comparison, that's suggestive of a problem. So here's our exhaust pulse setup. We've got a rigid, stiff hose in the tailpipe and our transducer, and then our cable going to the scope. And here's the exhaust pulse while cranking. Now here I did 5 seconds per division, which is way too much. Didn't need to go that far out. I could have shortened this up to 2 seconds per division. But because I had to run to the back of the vehicle, I wanted to make sure I'd get the waveform on the screen. So again, we are expecting relatively symmetrical segments here, right? Because this is a repeating pattern, and it should be symmetrical as the mechanical design of the engine is also symmetrical. We see double humps with similar amplitudes on the majority of these events, and then we have one that's kind of lazy or flattened out, right? That's weird, right? That is, again, we are measuring actual pressure pulses, actual high and low points in the exhaust itself, right? So it's important to keep in mind what these waveforms represent. Again, this is an actual transducer, not a delta sensor. So we see these flattening out here of this exhaust pulse. So after we've made that capture and we've seen our intake capture along with our relative compression, we feel pretty confident that this is a valve train related problem, right? I would say yes. Now let's look at in-cylinder pressure transducer waveforms. Now this is just cranking. We're not going to do a running compression test with this one. We're simply looking at the static compression when we crank the engine. So the first thing we're going to do is put our transducer in a good cylinder. A cylinder we know is not misfiring and not experience any substantial issues. So we put it in cylinder 5. The conversion rate on this transducer is 1 volt equals 100 psi. So we see it's outputting roughly 1.58 volts, which would be 158 psi. When we crank the engine, we did on this particular capture, we actually shortened up the time base to 500 milliseconds per division. We could have obviously zoomed out more, and that would have been just fine. So we have just around 5 seconds on the screen. But as we look at this, after the engine has been cranking for a good period of time, we can see it's very repetitive and symmetrical, and it's very rock steady. So now we're going to go grab cylinder 1. And we crank cylinder 1, and we extended out our time base a little bit just for dramatic effect. But we can see cylinder 1 is all over the place, right? We have points of higher compression where it's pretty close to cylinder 5, like 158. And then we have points where it's a little bit less, maybe like 130 or 120. That's not right, right? That's different. Again, symmetrical construction of the engine mechanically would suggest that we should have symmetrical construction of the waveforms. Makes sense, right? So let's zoom in a little bit. And as we zoom in, we see, sure enough, there are events that are actually maybe a little higher, and then we have events that are quite a bit lower on our total compression in cylinder 1. So we can see that we are, in fact, losing compression intermittently on that cylinder. So you're like, well, what's going to cause it to lose compression intermittently? Something in the valve train, I think we can say with confidence, right? We have enough data at this point that we can establish this is definitely a mechanical fault. We also feel confident that this mechanical fault, the origin is in the valve train of the engine. We also know that the PCM recognizes that there is a combustion problem in cylinder 1 and is subtracting fuel in an effort to even out the engine's running, right? That's what we saw in our scan data. Now, what we would do next at this point is recommend that the valve cover be removed for a mechanical inspection. Now, we're also going to discuss some common failure points on this engine platform and what should have happened on this when this vehicle was at the original shop that was working on it. What went wrong on this vehicle at the original shop that worked on it? They did not localize the origin of this misfire. What was the root cause, right? They failed to ascertain what the original root cause of the problem was. They also failed when this went to the machine shop. The machine shop should have advised this shop that was working on the vehicle originally of the common failure points of this engine and recommended or required replacement of some specific components, which we will go over in a moment. Many components were also replaced unnecessarily, which led to a greater bill to the customer that, again, was not justified based off of the information and the testing that we performed. Here is what is common on this particular platform. The 3.6 and the 3.2 have known issues with the valve rocker arms, which you see highlighted here. Typically what we see happening with this particular component is there is a little wheel on the valve rocker arm, and that little bearing wheel that's on there can actually seize. Now, there could be a variety of different failures, but the valve rocker arm is a self-contained assembly, and again, they suffer failures which cause them typically to drag or seize, which will damage the camshaft lobe. Now, that's not the only way they can fail, but that is one way they can fail. Now, what you'll see on these vehicles in most situations is this will start as either a misfire that will be felt when driving the vehicle or a ticking noise coming from the upper end of the engine. It is possible the engine will have one of those two symptoms. It is also possible that the engine may have both of those symptoms. But that is a very common problem on this platform, and so it's important to know this if you are diagnosing a misfire on these vehicles. This is just a picture example of one of these specific vehicles that experienced an extreme failure of one of those valve rocker arms. So basically you see the camshaft lobe is actually physically damaged on this vehicle, and we'll show you another picture here. So you can see the lobe is actually worn away partially as a direct result of that valve rocker arm. The small bearing wheel is not rotating correctly, and so it's dragging on the camshaft lobe and actually damaging the metal of the camshaft lobe. So if you have a valve train related problem like this, and you find that the valve rocker arm is the root cause, of course, if you have any of these engines apart, it would be highly advisable to replace all the valve rocker arms regardless, which did not happen on this vehicle when it was sent to the machine shop. So all those valve rocker arms have also been superseded by the manufacturer, which means there have been improvements made mechanically to address known issues with this component. Valve springs should also be replaced when the cylinder head is off like this, And lifters is also another component that would be advisable to replace on any engine cylinder head that has been removed with any reasonable amount of mileage. Now, if the camshaft lobe has been damaged and metal has gone missing inside the engine, like we saw in those example pictures, then it is very necessary to, number one, warn the owner of the vehicle that this could result in catastrophic engine failure because metal has gone missing inside the engine. And number two, if you are going to even consider repairing that engine oil pressure needs to be verified as above specification when the engine is fully hot and up to temperature before any repair is suggested or made. Now, this particular vehicle we worked on, there was no clear visual evidence of damage to the camshaft lobe or to the bearing or the wheels on the valve rocker arms. However, there was evidence of flattening on the little wheels on the valve rocker arms. And that's very subtle. That's an easy thing to miss if you do not look very carefully. But again, this vehicle has roughly 100,000 miles on it. Those components should be replaced, number one, because there's a known issue with them, and number two, because the mileage on the vehicle, when you remove a cylinder head and go to all that work, you should be restoring it to like new condition. So, this vehicle is a candidate for repair. There is no major missing metal, so replacing the valve rocker arms is an acceptable repair. Now, it might be a good idea to replace the camshafts just to be prudent. However, there was no evidence of substantial damage to any of the camshaft lobes at this time. So just wanted to kind of sum this up and note, when we're dealing with vehicles like this and we have faults of this origin, mechanical in nature, it's really important that we do our testing and document these things and verify the actual root cause of the problem. When we don't do that, it leads to unnecessary money spent, but it can also lead to major concerns down the road where a problem doesn't get resolved. Somebody has spent a lot of money here trying to resolve this issue, and now they have spent that money needlessly, and a lot of time was wasted and a lot of money was wasted. So you can see how we were very effectively able to figure out the root cause of this problem using our top-down Phoenix Smart as well as our top-down oscilloscope with some mechanical testing using a pressure transducer and an amp clamp and an ignition coil on plug probe. We were able to come up with very clear evidence that this was in fact a valve train issue. And of course, we also have all this documentation we can show to the owner of the vehicle to establish that this was the root cause of the failure. So hopefully you enjoyed this lesson on this vehicle. Again, this particular vehicle platform, keep this stuff in mind if you encounter one of these vehicles, and I would suggest employing these techniques on those vehicles in order to verify what the root cause of the problem is. And as always, we appreciate you taking the time to watch our videos, and please like, subscribe, and share. And as always, I'm Hawken with Top Don, and thanks again. We'll see you next time.